multidisciplinary, interdisciplinary workshop. Hopefully, we'll try to make some connections to other folks thinking from the computer science and AI side as well. So I wanted to start off by raising two fundamental problems in intelligence, and had several days of discussions and talks to go over each of these different topics. Like we had a talk about object-centric, unsupervised discovery, for example, and thinking about a lot about world models and possible definitions. And so what I want to emphasize here is that even though we spent a lot of time on, okay, what the definition of a world model is and how these updates can happen, firstly, in biological systems or organisms, there are metabolic costs. There are costs associated with the size of your brain in terms of how large of a brain and body and how to move that are associated with the neuroscientific problem of how to create representations, hold them in memory, and not just memories in the sense of remembering what happened in the past, but working memories in the sense of remembering where you are, what direction you're facing, and so forth. And the second problem is the problem of factorization, which I want to suggest is a promising avenue for thinking about how generalization might occur within a system like the brain. So rather than thinking of the brain as a system which has all of these biological constraints, in which computation is more naturally difficult, I want to take the perspective instead that from all of the constraints that evolution imposes and the constraints of movement and surviving and so forth, there are actually interesting algorithms that might have emerged as a result of evolutionary optimization, optimization over a lifetime, and that one result of that is the existence of modular representations that have factorized the world. So like imperfect, but good starting point is to think about prime factorization, or decomposing 14 into 7 and 2, in the sense that that is a factorization problem. It is easy to verify once you have it, but might be difficult to solve in more general settings. And the case in neurobiology would be the case of using past sensory experience or information you've learned about the world to generalize to new circumstances. To make this explicit, we can just consider this toy model where in vision we might have 100 possible different objects composed in 100 different rotations or different poses combined with 100 different colors and then forming a possible image. And of course, the real world is much more complicated than this. And yet, even with this simple model, there we have 10 to the 6 or a million different possibilities for objects that could be present in this model. But yet, this problem of inference seems easy once we can break it down into 100 plus 100 plus 100 kinds of internal representations, or 300 or so. So what this means is that once we have the right product space for representing this piece of information, we can solve this problem easier. Another example from perception comes from Adelson's, in this course it's not the checkerboard, but the box, where we can think of the fact that we see P and R as perceptually different, even though pixel-wise they have the same intensity values, as another result of our perceptual system performing factorization, where what we don't care about is the raw pixel value that's present to our retina, but rather about characteristics of the surface that we're envisioning, and we're factoring out properties of the illumination, which are not intrinsic to the particular object that we're seeing. So I just raised this as another intuitive example of where perception is involving this task of factorization. Another interesting example, I would say, is the case of navigation. So many of you might be familiar with the case of grid cells, which are found in medial entorhinal cortex and most thoroughly studied in rodents, where if we were looking at an animal as it's moving in a particular arena, and then looking at its particular action potentials, you can see that they're clustering in particular locations, and that these locations have this lattice-like structure that is occurring at multiple scales, depending on which neuron we're looking at. And then these neurons also have different spatial phases, so if you're looking at each of these as a different single unit with a different preferred tuning curve. The striking feature is that grid cells in the medial entorhinal cortex not only have this periodic organization, but have structure in terms of an underlying population. So the finding is from Sensola et al. Is that they are organized into modules, where if we look at the spacing between two of these peaks, and we look at the histogram of the spacing, you can see that the distribution is following roughly this geometric progression. There's been a lot of fun theory work on why that might be the case. But the takeaway point here is that you can think of these functional modules as encoding one of your positions modulo a certain value. And then there are multiple scales which are going to be useful. And then in order to hold this within working memory, there's been work on so-called continuous attractor network hypotheses. Continuous because it's representing space in this periodic but continuous way. Because of this periodicity, the hypothesis is that the weights are organized to lie along a torus of activity along this neural manifold. So this torus is a representation of your space in 2D. So, okay, that grid cells are cool. What's their purpose? What are they good for? So in the first part, I'll try and tell you about what is the benefit of this grid cell system, why the modules are useful, and how you can store these in attractor networks. And then I'll tell you a little bit about oscillations. So first, what are periodic spatial codes good for? So let's start with a simple example where we're just encoding different numbers, and we want to have, with some neural code, the best possible resolution that we can with a particular budget of neurons. So if we're starting off with a periodic code, we might just imagine we can have 3 neurons. So in this case, I'm just showing one of them that's just responding every third possible space. And yeah, you don't need to be a mathematician to realize that with n neurons, then you can encode n different positions. So you're just going to get nice linear scaling. If you have a second code, so in this case, this is repeating every fifth, then now we have 15 possible positions that we can encode, even though the number of distinct neurons or distinct units we would have is only 8. And yet, so we're going to have a repeat, of course, at every 15. But now with just 8, we can encode 15 possible positions. And hopefully you can see where this is going, where it's very easy to add another module. So now it's 3 plus 5 plus 7, so 15, and 105 will be the period at which they repeat. So this is to give you the intuition for how you can, with a very small number of neurons in a periodic code, generate a large combinatorial range. And some work by Lafitte has made this explicit by connecting these to residue number systems. So now more formally, if we're representing an integer in terms of its remainder value relative to some moduli, so in this case 3, 5, and 7, then we have an encoding. So it's a remainder code of a particular number. So 40 is 39 plus 1, so it's 1 mod 3, 0 mod 5, and 5 mod 7. And the nice feature about this code is that provided that we have the technical condition that these numbers are co-prime, then again, we have a range that's the product of each of these individual moduli. So in this case, we have a range of 105. And in addition to that, this is a useful code because the operations are very easy to parallelize. So if we're adding 2 numbers in base 2 or in base 10, then we have to have carryover operations. But in this case, the operations are carry-free. So you can perform them all in parallel without reference to each of the other modules. And this is just an arithmetic example. And the takeaway is that this is also an example of factorization in the sense of being a product space of the ranges of each of these individual moduli. So what this means is that now, with very small components or populations, possibly unreliable, we can construct a large combinatorial range which we wish to represent. So now, just to go over some of the technical details of how we're formalizing this within a population code. So within one grid module, we want to design a periodic population that's going to have a spacing or going to represent space modulo some particular interval. So we want the similarity of this vector to be one both at a representation of the same position, so it's self-similar, and modulo some other position. So the way that we're going to construct this up is quite similar to a Fourier transform, except it's going to be a randomized Fourier transform where our position of x is going to be represented by these complex numbers that are going to be spun by this value x. So what this means is that, so I think of a complex number, you can think of it as a real number and an imaginary part, or you can think about it as an amplitude and a phase. In this case, spinning these phases is not going to change their amplitude, so the only free parameter is the phase. So I'll refer to these complex numbers as phasors from now on. And what's nice about these phasor vectors is that you're able, by multiplying them, to add the arguments. So there's a nice algebraic framework from the residue numbers that are inherited within this population code. And then the next step is to say, if you have a population, one with mod 3, one with mod 5, one with mod 7, or you can really pick the moduli you like, then you can have an entire system that has a dynamic range of 105, even though each of these components are low precision themselves. So roughly, the analogy is that P is meant to be like a place code, which is going to be more local and respond to one particular position. and G1 through G3 are going to correspond to the grid modules. So now we have a nice code, but we need to still solve the biological problem of holding these values in memory and doing so efficiently. And one important point from thinking about brains performing computation is that individual neurons might be stochastic, but at that population level, there might be very deterministic or precise computations that can still happen. This is often in contrast to the way we think of conventional computing, where their operations are deterministic at the individual level of computation, and where it might be disastrous if we allow some degree of stochasticity to occur, because our algorithms aren't designed for that. So I think there's an interesting area of thinking about randomized algorithms that are enabled by these population codes. So an initial step we might have is to say, OK, well, we can know how to store all of these individual vectors within a memory. So we can just store 105 patterns within something like a Hopfield network. And this is a perfectly fine solution. It has just one fundamental problem, which is that if we want to create this network, it's going to, we know from studies of capacities of associative memory that the dimension we're going to need for these vectors is going to scale with the number of patterns that we're storing. So we've created this nice compositional system, but we haven't gotten the most out of it in terms of an efficient representation that's able to encode all of this information. So instead, the proposal is to say we can use this relationship that, in fact, our place is equal to G1 times G2 times G3 to create a self-consistent representation that's only going to work on these individual modules. So the intuition is that if we have some signal for the place code, and we have signals from these other grid codes, they might be perfect or imperfect, or they might be perfectly accurate. If we want to infer G3, we can divide out G1 and G2, or multiply by their inverse, to get this value out and solve. So this is, in fact, what this equation is doing is it's multiplying by the inverse for all of the other modules, taking an outer product matrix, as we do for associative memory. And now, instead of storing 105 patterns, we can just store 3 plus 5 plus 7, or 15 total, which is going to be much more efficient in terms of the number of patterns that we're storing. And roughly, happy to chat more about the how this maps onto neuroscience. But you can think about this again as corresponding to grid set codes and place codes, where we know that we have recursive interactions or recurrent interactions between the hippocampus and entorhinal cortex, and modules are coordinating with each other and with the hippocampus to update their estimates of position to be self-consistent with each other. And what we find, oh yeah.
I just want to ask a question that I'm always confused by in this kind of context. So, like, what happens if your representation slips a little bit? Like, if you keep your knowledge mod 3 and mod 5, but your representation mod 7 gets off by 1, then the entire representation is ruined. And this seems to rely on some kind of dead reckoning. So if a rat is wandering around in some box, it might slightly lose track of stuff. And maybe the mod 7 neurons might get a tiny bit off. And yes, so what's your account of this?
Okay, I see. So there's like two parts of like questions. One being like, okay, error correction, or how does it account for like error correction? And then also like, yeah, in actual navigation where there are errors present, like how do you correct for that, or what would be the mechanism?
Yeah, I'm just asking about the robustness of this kind of system. Yeah.
Yeah. So on the first part, there's a difference on if the degree of error is like within an integer or greater than an integer. If it's less than an integer, then there's a mechanism you can show for how to just go to the nearest number and correct. If it's greater than one integer, then your solutions either need to be error correction in the high dimensional weight space, or there are nice ways in which you can combine these Chinese remainder theorem codes with error correction methods, where if you have a redundant moduli that's used as kind of a error correction bit, like in a Hamming code, then you can actually recover some degree of errors from this kind of system. As far as like how the brain might be doing this in the case of like navigation where there's drift and errors and so forth, of course this is also an empirical question of how animals or rodents, for example, might do this. So local cues, so egocentric visual cues, border cues, other sensory cues, right, are one common way for solving things. But I also think that there's internal network mechanisms that are able to resolve some noise of individual units. I hope that's helpful. Okay, so just to make the point explicit about the scaling, so if we have some patterns, so 100 patterns spread across multiple modules. If we have, say, 2 modules, we could split that into like 49 and 51 and get approximately 2,500 patterns, or about 33 cubed possible patterns. So this shows that with this modularity, we have less patterns, or we need less memory to encode a large combinatorial range. But in addition to that, what we find is that if we're looking at the dimension of each of the patterns that we need to store, so this is, so your total memory cost is the number of patterns times the dimension of the pattern. The dimension that we need is going to scale, so if we have a particular dimension and we have a particular number of modules, then our capacity is going to scale superlinearly according to our dimension. So we're getting better than linear scaling in terms of the dimension and the range that we're able to encode. And the rough back of the envelope calculation for this scaling is that it's about k over k minus 1. So as you have more modules, then this is a more difficult factorization problem. Consider a factorization problem where you have to decompose like 7 integers being multiplied together. But in return, if you have that, then you get less storage that you have in your network. But you yeah, so there's a trade-off between how large your dimension needs to be and the storage, but you're still coming out ahead relative to conventional associative memory. And then in addition to that, we also checked for cases of noise robustness, so whether that noise comes from external inputs or whether it's intrinsic to the dynamics. So the key thing is that because these are circular variables, we use von Mises noise. The black curve is showing the capacity and its eventual fall off with coding range for a fixed dimension. And the cases for input noise, or for extrinsic noise and intrinsic noise, you can see that, of course, the capacity is going to go down earlier, but it's still relatively robust because of these attractor network dynamics. So there's a lot more to say in terms of particular applications for things like navigation or episodic memory, or in terms of tying things back to the hippocampus and entorhinal cortex. But I wanted to end with a last bit, which is thinking about oscillatory dynamics, which of course play a big role in the hippocampus and hippocampal like theta, for example. And I think there's generally a more fun question about how to compute with oscillations. And we were inspired by this work on, for example, oscillatory Ising machines, which are meant to solve combinatorial optimization problems, such as KSAT problems. And the key idea, which is pretty cool, is that rather than having an Ising machine that has to make an immediate decision on when to have -1 or +1 as its particular state, instead you have a continuous relaxation of the problem where in the long run it settles to one of these states. But in the meantime, it's allowed to settle, or allowed to oscillate or go to either 0 or 180 degrees phase. So these end up to not only just provide interesting algorithmic insights into solving these problems, but also might be implementable on new kinds of hardware in which naturally can compute according to these oscillatory dynamics. And then Connor Bybee and collaborators in the Redwood Center took ideas from this to go from oscillator Ising machines to higher order Ising machines to make solving these problems like KSAT even more efficient in terms of the overall search. So if we take our network, which we had in discrete time, so simplifying this again, where we have some nonlinearity that is like a sine function quashing down to unit amplitude, and then these internal dynamics here. So I'll just call this a pre-activation term H. And then we just perform a simple change of variables, where now phi is just the argument of this complex number G, applied element-wise to each element in this vector. Now we apply these dynamics in phi over the phase directly. So this is kind of like a Koromoto oscillator, except we also have this term H that's outside of this term. And the H term is just the same as we had here. So the dynamics are almost as close as possible as they could be to the discrete time version. And yet, because we have these dynamics more continuously evolving over time, we find that this network is increasing memory capacity. So it turns out that if we're comparing the discrete time dynamics in the dashed lines versus the solid lines for the continuous time dynamics, same color means the same dimension. The accuracy fall off in terms of being able to solve this factorization problem for the same dimension is a little bit later. So it indicates it's able to solve these problems. And we did some investigating. Why might this this to be the case. This seems highly non-trivial that just a simple change would make a significant difference. And it turns out that there's some fun things we can look at into the energy landscape where this is the class of problems where continuous time dynamics tend to do better. And you can see in this kind of case, I call it a benign unstable regime because it's still drifting, but staying within the right basin of attraction, whereas other networks with more discrete jumps are falling out of the right basin of attraction. And so they're getting into loops where they're not converging to the right solution. So there's actually some, I think, interesting problems here of like further getting into analytically why this might be the case. But we basically found this middle regime where instead of both networks succeeding or both networks succeeding or both networks failing, one succeeds and one doesn't because of this small difference that makes a practical difference. And in the spirit of showing for combinatorial optimization, we can also show that we can solve the subset sum problem. So this is whether or not there exists a subset of the set of numbers that sums in a particular integer. So when the integers are all positive, then this is a NP hard problem. And here 3, 17, and 22 is one subset that actually exactly satisfies this constraint. And the network is able to solve this type of problem. So this is just going back to, OK, we can solve the same kinds of combinatorial optimization problems. So in summary, first thing, as a high level, I want to propose that this factorization is critical to perception and cognition, especially if we want to understand how it occurs in imperfect and bounded agents like ourselves and other animal species. Second, we have these associative memory modules that are compositional in the sense that they're explicitly forming this product space, which can then be flexibly recombined in different ways to solve these factorization problems. And then we show a bit about how the oscillatory dynamics, which are also observed prominently in many biological species, can improve convergence in these cases. And then just to talk about some connections to related fields. So hopefully this is the start of a discussion rather than the end of it. Firstly, there's a lot of exciting experimental neuroscience that's revealing new evidence for modularity, multiplicative tuning in grid cells, and looking at grid cells and higher order spaces. Secondly, in neuromorphic computing, or this article I'm quoting their title, Neuromorphic Computing at Scale, they say that we need to think about new kinds of algorithms that are going to work for neuromorphic architectures that are distributed, that are robust to error, and that ultimately might take not just shallow inspiration from the brain, but really get at the same underlying principles. Third, I think that there's insights from theoretical computer science and sketching algorithms and random projection residue number systems and so forth that can provide formal guarantees for these kinds of algorithms. So because we can build these algorithms from the ground up, we can really understand and develop not just insights from biology, but insights from proofs and use tools from computer science to make formal statements or guarantees about the properties of these systems. And then lastly, associative memory, periodic codes are commonly used in AI architectures as well. And so it's useful to think, in what cases are there actual meaningful cases of convergence as well? So with that, I'll leave you with, these are the two papers or areas where you can read more about what I talked about today, and along with some additional information. This is just to say thank you to the Redwood Center and to the neuroscience program at Berkeley. And this is to say thank you to the funders and to you for your attention. Happy to take any questions.
Is there evidence for such oscillatory dynamics in the brain?
I would say so. So in the hippocampus, for example, at least in the rodent literature, there's a huge role of hippocampal theta, so around like 8 hertz, I would say. And this is a huge role in mediating when spikes are firing and also what their timing might be relative to this oscillation. And then because it is a relatively short window, it has a nice ties to spike timing dependent plasticity potentially for.
And do you think these are constant oscillations across different people, or each person has their own oscillations, or what?
Oh yeah, so
frequencies?
I'm definitely oversimplifying in the sense that there's multiple scales of oscillations that different neuroscientists are looking at. It's not like the theta is a constant that's happening. There's variation depending on whether there's locomotion or not.
No, but is it significantly different different between different people, or would it be sort of universal oscillations across different brains?
I think that roughly speaking, the kind of like bands or the different like power laws that people see about the oscillations are roughly pretty similar as to whether or not the same oscillatory dynamics are happening when two people are performing the same task. That's the more fine-grained question. I'm not sure, but it'd be interesting to investigate. Yeah.
What about the time scales? How does the, let's say, size of the factor, if you have like 17 steps to go, does that influence the time scale for your inference of the factors?
Oh, yeah. So definitely the initial similarity, or how close you are to the right like Bayesian of attraction, definitely matters. And then also the search space matters. So I can show you plots of like what the convergence time looks like under different problems.
Do you converge faster if you add the oscillatory dynamics to it? We get
It becomes a bit of apples to oranges on how to compare like discrete time and continuous time. So to make it a fair comparison for number of time steps, you can use continuous time with adaptive step size solvers, and then it looks pretty comparable. Yeah, though it's still a little apples to oranges. Good question.
Thank you so much. May I have your...
I'm so sorry. Yeah.
Literally. Okay, and now we're going to do something completely different. He's going to take time. Sit here. We are going to have a series of lightning talks.